So welcome all. TCS seminar at Jagiellonian University. We're happy to have Colin Geniet. Colin finished PhD in
just
24.
Yes.
25? 25?
24.
No, 24. So not this year.
Less than 1 year ago.
In Lyon, right? With,
yes.
Under supervision of Stéphane Thomaset. And now you're a postdoctoral researcher in Korea at the Institute of Basic Science in the Sangyus group.
Yeah.
Okay, so and your research interests cover what? Graph colorings, definitely. So kind of merged with. Okay, merged with is a new thing. What did you do for your PhD? Can you tell us?
I was doing twin-width, and that's a new version.
Okay, we're happy to have you here. The floor is yours.
Thank you very much for the introduction, and also thank you for accommodating the double seminar today. So, I'm going to talk about merge width, which is some very recent notion from Jan Dreier in Vienna and Dreier and Toruńczyk in Warsaw. If you take the average of both cities, I think you get that it comes from Krakow actually. And this is actually from this year. So, okay, let me say a few things about the motivations for merge width. Jan and Shimon have one problem which interests them currently, which is the model checking problem for first-order logic. So model checking, it's an algorithmic problem, which is you are given a graph G and the formula phi, a first-order formula. You want to test if your graph satisfies this formula. Okay, and I won't give any precise statement, but they prove that for graphs with bounded merge width, there is an efficient, in the sense of experimental tractable, algorithm for this problem. Okay, if I just tell you that and not what merge width contains, it's not very interesting. So what has bounded merge width? Well, the point of the notion is that it generalizes two things. On the one hand, you have the notion of bounded expansion, which is a very famous notion of sparsity. So famous, and it's a very general notion of sparsity. So for instance, it includes bounded degree classes. Oh, by the way, I should clarify, what I'm writing here are properties of classes of graphs. And this is just inclusion diagram. I think it will be the only poset I draw in this talk, I'm sorry. So bounded degree has bounded expansion, also anything which is kt minor 3. Okay, so this is the first side. But this is a notion, this is about sparse graphs. Merge width isn't. Merge width contains dense graphs, and in particular, it generalizes twin width. Which itself generalizes click width. So these two things are incomparable. Here you have dense things, like for instance clicks, which you don't want for sparse graphs. And the other way around, it's highly non-trivial, but bounded degree graphs don't have bounded twin width. And for both of these notions, there were algorithms for this model checking, which were known. The point of merge width is to unify these results. Okay, that's all I will say about this logic side of merge width. What I want to talk about is some much more concrete and combinatorial questions, namely hh-boundedness. And I will try to show you some simple techniques to manipulate merge width. Yes, you can put this in also. So there's a non-trivial intersection between the two. It contains this in particular.
Whereabouts does bounded flip width fit into?
Good question. So flip width is above, but conjecture to be equal. the flip width is the same thing. It was designed as a generation of both of these things, which is well behaved for logic, but this wasn't known. This isn't known for flip width. And you could add things like nowhere dense, and then the generalization would be monadically dependent classes, but I don't want to get into that. I want to stay with reasonable graph theory. So let me start with the definition. I'm going to lie about the definition and then fix it. So if you see something suspicious, don't panic. So the way merge width is defined is I will give you some process to construct graphs. So the way we do it is you start with some partition P, and so P, there will be indices which correspond to some time steps, and initially it's just the partition into singletons of the vertices. And you also start with some set of edges, which initially is empty. Okay, and now to go from Pi and Ei to the next step, you have two possible operations. The first is that you can merge two parts of P. And the second is that you can create new edges, and the way you will do it is you pick two parts and add a biclick between them. So you add x times y to I for some parts. Xy in Pi. And as you are allowed to do it with x equals y, then you add a click instead of a biclick. Okay, so if I don't tell you anything else, you can make any graph in a very stupid way, which is when you have your partition into singletons, and you add edges one by one, whatever you want to put, and that's it. So of course we need to add some constraints, so I'm going to define some kind of notion of cost for this. Okay. So I will call it the width. Oh, sorry, by the way, this thing, this is called a construction sequence. So the width of this construction sequence, it's some number parameterized by a radius r. And it's defined as follows. You take the maximum over all time steps I and all vertices of your graph B. And now you look in the current set of edges at time I at the ball of radius r around your vertex. And what you count is the number of parts in Pi which intersect this ball. Okay, so now if you think about this stupid construction sequence, okay, what is the number of parts in the, let's say you look at the very last moment because it will be worse. So you take some ball around your vertex, and it's for the last set of edges, which is just the actual set of edges of the graph. And you count the number of parts in the intersect, since they are singleton, it's just the size of the ball. So for this number to be bounded, you want the size of the balls to be bounded, or in other words, you want your graph to have bounded degree. So this stupid construction sequence is actually the proof that bounded degree graphs have bounded merge width. At this point, I should tell you what actually bounded merge width means. So we say that a class C of graphs has bounded merge width. Oh, I did not even define merge width, sorry. Doing things wrong. Let me put it there. So the merge width for a specific graph, and again there's this radius parameter, it's just the minimum width at radius r, and the minimum is over all possible construction sequence. Okay, and now I can define bounded merge width. And if you are familiar with, for instance, bounded expansion, it will be exactly the same kind of definition. So we say that a class C has bounded merge width if there exists a function f such that for any graph in your class and for any radius r, the merge width at radius r is less than this function. Oh. Yes, question?
Just one question: when you're going from I to I plus 1 in this sequence, you always keep the previous edge, or not about to remove some edges?
We never remove edges now.
So EI is always included.
Yes, this will be, so PI will be monotone in the sense of coarsening, you always merge things, and EI is increasing. Any other questions?
How does this differ from the construction sequence for the notion of click width? I'm not asking about the width definition, but the sequence itself looks similar. Yes, we are merging, or we are introducing some homogeneous.
Okay, I think I see what you mean, but for click width, so for click width, in a sense, you always have only a bounded number of parts, but sometimes also you will take two graphs and combine them. If you wanted to rephrase click width in terms of this kind of definitions, you would need that the connected components have bounded size. And it's not just the connected components, it would be connected components in the quotient graph. I'm not sure if that makes sense. You have your current set of edges, you take the quotient by the partition, it gives you some new graph. You need the connected components of that to have bounded size, sorry.
Okay. But the operations are the same. So I can merge and I can add the complete bipartite.
Yes, in a sense. Okay, let me make an example which is slightly less silly than this bounded degree, where we actually need to merge stuff. I'm going to do it for degenerate graphs. So you take some degenerate graph, which means you have some ordering of the vertices, such that for each vertex, if you count the number of neighbors on the left, it will be less than some constant k. This is called k degenerate. And they don't have bounded merge width, but I claim that in that case, the merge width at radius just 1 will be, I guess, k plus 1. Okay, so the way we do it is, so initially we have our partition into a bunch of singletons, and we are going to start merging them from the right. So if I'm somewhere in the middle of a sequence, I will have a partition which looks like that, a big interval on the right, and then just singletons. Okay, and I also should tell you which edges I will have at this point. So let me just move that. What I want to do is have every edge incident to this big part. So maybe the graph should have some edge in here, but I will not have created it yet. But any edge incident to somewhere here should be present, and also is inside the part. So first thing first, how can you, this is actually a construction sequence, so how do you move to the next step? Well, you look at this next vertex. It has a few neighbors to the left, so you create these new edges, like maybe like this. and then you extend your partition by merging this singleton with the big part. Okay, now I need to show that each time it's not that the neighborhood is small, but the neighborhood intersects few parts. Why is that? Well, two cases. Your vertex is on the left. Then the only edges, I did not create any edge between two singletons. So the only edges will be between this one and the big part. So there's only one part. Second case, you care about a vertex which is here, like for instance this one. Okay, then it might have some edge inside the part, that counts just for one. What could be an issue would be if there were a lot of edges to singletons, but they are all on the left. So by degeneracy, there's only k of them. So you get this bound k plus one. Bounded expansion, in some sense, it's saying you have bounded degeneracy at every radius, with a bit of imagination. So sort of the same kind of arguments shows that if you have not just bounded degeneracy, but bounded expansion, you get some bound at every radius, and you have bounded merge width. Twin width, I don't want to define twin width, but I can just mention that if you want to modify this definition to get something which is equivalent to twin width, what you would do is, instead of saying you look at each vertex, you will look at each part of your partition. If you just make this transformation, you get exactly twin width. So that's all I will say about that. Okay. Now, I told you that I lied about this definition. There's a big issue with it, which is it's not closed under complementation. If you have your graph, you replace edges by non-edges and vice versa. There's no reason that the merge width would stay the same, and in fact, it's not easy, but you can show that it's not, bounded merge width is not stable under complementation with this. And we're not happy about that because one other nice property of merge width, which I did not mention, is that it's stable under transductions, first order transductions. And taking the complement is really the most trivial example of transduction you can think of. So what is the problematic example? Well, okay, let's say we had some bounded degree graph. I'm going to make one which is a bit too simple to be an actual issue, but it's just as an example. Here's a bounded degree graph. Now think of the complement of that. If you want to construct it with this, it's quite, you have a lot of edges to create, and you need to somehow dodge the few non-edges. You can do that because it has bounded twin width. But if you take a bad bounded degree graph, you will not be able to do it. So what would you like, how would you like to describe the complement of a bounded degree graph? Well, it's quite easy. What you would like to say is, this is not an edge. Right? This is also not an edge. This is not either. So you do all the non-edges, and then you take this big part and you say whatever remains is an edge. Well, this is exactly what we are going to do in the definition. So I need to change a few things. The main one is that there will not be just this set of edges, there will also be non-edges. Actually, let me do it in here. Yeah. So there will be a set n of non-edges, and initially it's also empty. So initially, you have a bunch of pairs and you don't know whether they will be edges or non-edges. Okay? And now you have a third operation. So you can still merge parts. You can add things to edges. But you need to be careful. If you say that something is a non-edge, you can't turn it into an edge. So what you would actually say is you add your pair minus the current set of non-edges to the edges. This operation is called resolve positively. This, we say it's a set of resolved edges. So we add new resolved stuff, and positively because we are adding edges. And the other one, of course, will be symmetrical, which is you add things, I'm lacking a bit space, sorry, but you will add things to the non-edges And of course, you can't turn an edge into a non-edge. And this will be called resolved negatively. Okay, last thing I need to fix is what is this ball here? I took it in the set of edges. Now I will look at the set of edges and non-edges. It doesn't, I don't care about the distance in the actual graph. What I care about is the distance in the set of pairs for which I fix some behavior. So this, yes. Sorry, Ni. Yes. I mixed up with the next thing, which is, take a bit of space here. I will have a set Ri, which is this union. And R here stands for resolved. Okay. And with this, you can do exactly what we described here to get the complement of the graph.
So what do you mean distances including the non-edges?
So really what I should write here is, you think of this set as a set of edges for a completely different graph, and you look at the distances for this.
So you treat the non-edges as edges?
Yeah, exactly. You already have two different things, which is the graph you're trying to construct, which is probably not interesting in terms of distances, and the graph of resolved pairs, which is where you look at the graphs and you want them to be small.
But then when you stop these unresolved edges, they become what?
Oh, so when you stop, you have a few ways to do it. Either you say you are only allowed to stop when you don't have any unresolved stuff, or you just say in the end you keep this set E, and this becomes the two edges.
This ball is like, then you're talking about a click there, right? If you do Ri.
Yes, but at the end you will have only one part probably, or a bounded number of parts, so it will be fine. So, okay, precisely for the complement of boundary, you add all the non-edges, then you merge everything into a single part, and you resolve positively this part with itself to make the click. So in the end, indeed, this is a click, but you only have one part, so it's fine. Any other question? Okay, so let me start talking about chi-boundedness. Who knows what is chi-boundedness? I should give a reminder? No, it's fine? Okay. So yeah, I could mention why did we look at chi-boundedness? Well, for bounded expansion, it's trivial. They are not just chi-bounded, they just have bounded chromatic number. And for Toruńczyk, it was fairly well-known result. So there's just a general game of take result for expansion, bounded expansion and Toruńczyk and generalize them. So I will try to do most of the proof. And I will start with a special case, which is not just for fun, it's actually used as a lemma. So I will say that a construction sequence this is not, sorry. Let me erase this, this is not very important. Yeah. So I say that the construction sequence is structurally, it's a bit weird name, but omega bounded. If it satisfies the following condition, whenever we resolve positively two parts x and y, then we need to have that x and y are independent sets And its independent set not with regard to the current set of edges, but with regard to the actual graph we will have in the end. The reason I call it structurally omega bounded is omega for me is just the click number, maximum size of a click. And this is a condition which guarantees that your graph does not contain a very large click. If you have a merge sequence with bounded width and this, you won't have a large click. So this I will not use, but let me prove it because it gives some intuition. So under this assumption, the maximum size of a click is bounded by the width at radius 1. Okay, I only need this to prove it. Take a maximum click in your graph. And in the construction sequence, I'm going to look at the last moment where all the parts, all the vertices of this click are in different parts. Okay, so it means the very next thing I will do is merge two of these parts. Right? Now, once I've merged them, it's not an independent set anymore. So I'm not allowed to use a positive resolve operation for this thing anymore. Which means I can't create new edges incident to it. So before I merged it, I needed to, so this will be the click in the actual graph, but I'm not sure whether or not they are already in this, this set of edges. But this argument just told me, actually, if I'm going to merge these two parts, every edge must already be present. So I will draw in red the edges which are already in my resolved set. I know that all of these need to be already present. So in particular, every edge incident to that one already exists. And now, since all the vertices of a click are in different parts, in the neighborhood of this vertex, you have the entire click. So the merge width at radius 1 needs to be as much as the size of this click.
So this is width, but with only this omega bounded sequences.
Yes, for when I look at the sequence with this condition, I look at the width of this sequence. This is why I wrote width and not merge width. I'm looking at the width of this specific sequence. I will get this bound. Okay, now here's the thing which I am actually going to use. Still under the same assumption, the chromatic number is also bounded, but this time I need to look at the width at radius 2 instead. Okay, now this is a really interesting technique which comes from twinning, actually.
So can I
Yes.
just interrupt? I still am stuck. I don't see something simple with the definition of the width there. So this is maximum over I and B, and the number of points in a single part PI is in the ball. Or it's a number of.
It's the number of parts of the partition which intersect this ball.
And what? So this max is over I or not?
The max is over all the time steps and all the vertices.
Time steps. So this is not PI there. This is.
It is PI because it's the partition at time I. Also looking at the resolve.
Oh, I see. Okay. Yeah.
Edges.
Oh, see. Understand. Thank you.
Yes. Okay. So this is something which is called the freezing technique. So what I'm going to draw is a graph where on the one hand I have the vertices of my graph, and here I have time. And I'm going to draw the partitions. So initially we have singletons. And okay, I'm going to cheat a bit in the drawing, and I will allow to merge several disjoint pairs at the same time. It's not actually a big issue. You can allow that, and it won't change the definition very much. So we get some drawing like that, maybe. So this is a representation of the partitions in your construction sequence. You can think of it as a tree where you just order by inclusion. And now the freezing technique is just looking at the maximum parts in this thing, satisfying some interesting conditions. So I will give you the concrete condition which I care about here. I say that I will freeze a part at the last moment in which some positive result happens. It is involved in a positive result. Okay, so maybe let me draw positive results in the yellow, so you can think of them as being edges horizontally here. So maybe, for instance, we added this thing and also this one and things like that.
So you only omega bounded sequences here.
Sorry?
On the omega bounded sequences.
Yes. Yeah, and still under the same condition. And yeah, for each vertex, I look at the last moment where one of these positive results happens. So this gives a new partition P. And for any part in this partition, you get three important conditions.
So what is the new partition?
Okay, sorry, let me say it again. So for each vertex, you progress in time, so you see a bunch of increasingly large partitions, and you look at the last one for which we did a positive result. And this is when we say we freeze this part and we keep it for our new partition. So,
okay, so
yeah, it's just
the new partition will be like consist of this frozen.
Yes, for each vertex. So, for instance, in this example, you would take this one. This one. This is not maximal, right? But this one is. This one was not maximal. This one was. And I guess these two are. You might have a stupid case which is isolated vertices. I mean, we don't care about isolated vertices, but then you just take the singleton instead. Okay, so we get three conditions on them. The first is that they are independent sets. And the reason is by definition, it is involved in a positive result. And the assumption is that then, for that to happen, it needs to be an independent set. So this was just the omega bounded assumption. The second thing is, so, okay, let's say P was frozen at time I. And maybe I should ever do that. Let me draw the partition at time I. So we have our part P, which we care about, and other parts. And we know we just need a positive result, so we have some a full bicyclic of resolved pairs with some other part. So what this means is, suppose now that your part P is adjacent to something else. And this is an edge in the actual graph. We know that in the future we are not going to add new edges, otherwise it will not be maximal. So this edge is actually resolved. Okay? So now I look at all the parts at time I to which P is adjacent. I know that all of them will make some resolved edge. And now pick a vertex not in P, but in this other part to which it is fully adjacent. This is my V. And I'm looking at width at radius 2. So I need to look at the ball of radius 2 around V in the graph of red edges. Well, this contains all these things. So what I'm just saying here is, in the partition Pi, the number of parts adjacent to P is bounded.
So P is one of the things that are frozen.
Yes.
And I is the moment when it gets frozen.
Exactly. Now,
okay. The number of parts that you are adjacent to, and this is real, edges in the real graph now.
Yes, it's edges in the real graph because of this thing that if you have an edge in the real graph, it needs to be already resolved. Otherwise, it will not be massive. So this is in the partition at time I, which is when I froze P. But that's not the partition I actually care about. The partition I care about is this partition P. What does it look like? Well, you will have some parts which were frozen after P. So that means potentially they became larger and they will look like that. And you will also have some which are smaller because they were frozen before. They might look like that. So in this partition, so this was for P. For P, the degree is not bounded. But what you get is that if you look at the parts which were frozen afterwards, they only became larger, so the number of adjacent parts can only decrease. So what I'm proving is degeneracy. If you order the parts of P, forget that, P ordered by freezing time, is degenerate. In the sense that the quotient was degenerate. So now I have a partition into independent sets, and the quotient is degenerate. That means the chromatic number is bounded. And if you check the bound, you should get the correct thing.
So I missed one thing. Why in the first place this degree was bounded of P?
Oh, here?
Yeah.
So we have this vertex V. So, sorry, first we know that we created a biclip with some other part by doing the positive result. I pick a vertex V in this other part, and now I know that for any part incident to P, I can go to P and then to that part in 2 steps. So the ball of radius 2 around V will intersect every part which is incident to P. And by this number of parts must be bounded. This is the definition of width at radius 2.
I see. And you order by freezing time, but the edges that you send, the things that are frozen later, so it's in the reverse time, no? What is
I'm not sure. I always mix up the direction for degeneracy, but maybe let me draw it here. Let's say this is our part P which we care about.
Yeah.
We know that it is incident to few parts. Okay, this is not a correct example, but it is incident to few parts at this moment. So it will be incident to even fewer parts if we move up and we start merging more stuff.
Yes.
Okay. So we did this special case, and now we need to reduce the general case to this. So, and when I told you this freezing technique is important, I wasn't lying because I'm going to use it a second time. But the only thing which will change is it won't be the same freezing condition. So now we have okay. I want to prove high-boundedness, so the chromatic number of G is bounded by some function of the clip number and the merge width. And once again, the only thing that will matter is merge width at radius 2. Okay. So we apply again the freezing technique. but this time we freeze just before getting maximum click. So let me say T is the size of the maximum click in G. And we freeze at the last moment. So we freeze the part P at the last moment such that P does not contain a click of size T. And okay, I should not say P, it's really the actual graph induced by P, not the current graph. The graph at, the induced graph at the very end. Okay, so we have the same drawing here, except I don't care about this positive resolve. I just ask, I have a vertex V. What is the first moment where a click of size T will appear? Well, I stop just before that. So once again, it gives some partition P.
Sorry, what do you mean by the induced sub, so G sub induced by the partition? Okay, so this is induced into like, are you freezing it at that time?
A part, yeah. P is a single part. Like
Oh, P is
Yeah.
a single part. Okay, sorry, that's a single part. Okay.
So a more formal way to write it is you pick for this P some part P at time I, if the corresponding part at the next time step would contain a click, but this one does not.
Okay.
And just the point is containing a click in the final graph, not in the current graph. Okay, so I get a new partition P. And now what I'm going to do is split edges into 3 kinds. And so it will give superposition of 3 graphs, and I only need to color each of them independently.
So you do induction on omega?
Of course, yes. So the first kind will be quite simple. It's the edges which are inside one of these parts. Inside some part P of my partition. And if you look at this graph, omega decrease, it's smaller than T. Okay, you need to do a very small amount of work to say that the merge width at radius 2 did not, or at any radius did not increase. That's just because it's a disjoint union of induced subgraphs. So we just apply induction on omega. Okay. Now I look at the rest of the edges, so I will ignore now. So I assume that every part in P is an independent set because I already got rid of these edges.
So this will be product coloring?
Yes. So I have 2 kinds of edges remaining. There's the one, in a sense, they're the one which were created before freezing and the ones which were created afterwards. So I will say ER, where R stands for resolved. It's edges created by positive resolve of X with Y. And I want this to happen before freezing. So I will only keep them if X is contained in some X prime and Y is contained in some Y prime, which are parts of P. So if you think that this time these frozen parts are the ones just before getting KT, for instance, this is a bad example because let me make it here. The edges created by this I would not pick because this happened after freezing, but this one was before freezing that part and also just at the same, let's say this counts as before freezing this part, so I would keep this in this set. Now the claim here, which you need to check, it's not very hard, is that this satisfies this condition which I put above, structurally omega bounded. So more specifically, what I just wrote to this here, it actually describes the construction sequence for ER, which is just, you do the same construction sequence, and whenever you do a positive result which does not satisfy this condition, you skip it. And you can check that with this, this condition, you satisfy this property. The reason is quite simple. You only do a positive result if you have this. So your two things are contained in parts of P. And we already got rid of the edges which are inside a part of P. So X and Y are independent sets. So this is structurally omega bounded. Well, really, I should say there is a construction sequence which is structurally omega bounded. So we already know how to deal with that. Okay, so now I have the remaining things.
So you say we disregard edges inside of P, but this must comply with the sequence.
Yes, so
it
it works because you can just say, okay, I could add a condition here, which is if x prime is equal to y prime, I also skip it. Yeah. Right? Yeah. This exactly corresponds to the edges in the first step. So now you need to deal with the remaining edges. So imagine you have your part P, and you know that it was frozen at time I. And now imagine you look at the partition just after that. So it will become bigger, and this creates a clique. Let's say this is my clique. Okay. And now I'm going to look at what happens in this partition, mi plus 1. So let's say you have a...
So both pieces, so in this part, no. So I want to say that this larger part that you created, so P is frozen just before, but then there is some other business that merged to this. But this might have been frozen even before, because there could be click already there, right?
It could have, yes.
Okay, so, sorry.
Maybe the click is entirely on the outside of P, but that won't be an issue.
Yep. Okay,
so I look at a different part. And I'm going to add one assumption, which is there's again going to be a JGRAC argument. So I'm going to assume that this is frozen after P. Now, let's assume there is an edge between P. I really want P and not this bigger part. P and this part here. And assume that it is in this set of U. U is for unresolved, of whatever remains. What I claim is that, so let's say this is my edge x, y. I claim that xy is not resolved at time I. Because suppose it were resolved, we know that at time I, P was, well, it's the moment we froze P, so it still counts for this condition. And this other part is frozen afterwards. So actually it would satisfy this condition. So that's not the case, it is not resolved. Okay. Now, there's a simple remark about construction sequences. See, if this is not resolved, but this is an edge in the graph eventually, it means we will do a positive resolve between these two parts. So now imagine you have some other pair which is also not resolved. Well, when you do this positive resolve, it will also become an edge.
If you resolve it later, then you are merging it with a click KT already, right? That shouldn't be possible. You already have KT on the left, you cannot positively resolve with anything.
That's the point I'm trying to make. So you know that I think you can take any vertex here, it does not matter, but you could pick Y, for instance. It can be adjacent to the interclick. This is a maximum click in the graph. So it is non-adjacent to something, for instance, to this vertex. Well, it can be that both, we know that this edge is not resolved, and it cannot be that this non-edge is also non-resolved. Because then whenever you do the next resolving step, they would both become the same thing. So this is a general, very important basic fact from construction sequences. If you have two unresolved pairs between the same two pairs, two unresolved pairs between two parts, either they are both edges or they are both non-edges. So we know that there must be a non-edge, and we know that it must be resolved. Okay, now look at a different part. Same situation, there will be a resolved non-edge, but maybe it will be for different vertex of the clique, and so on. But there's only so many vertices for the clique. So if I have a very large number of parts here, which are all adjacent to P, it will create a bunch of resolved non-edges towards the clique. And well, we know that merge width is bounded, so there can't actually be too many parts. So you get a bond which is something like the size of the clique times the merge width. And you need to be careful because it's only for the parts which are frozen after, but you end up with the same type of degeneracy arguments, and you get again that this is a partition into independent sets. P is a partition into independent sets, and the quotient of this by P is degenerate. So this is how you color the third set.
So that was mentioned, that was with one that you used here only.
Here I only use with one. The only place we use with two is for this proof. So actually, yeah, I'm almost done, so let me just mention two questions. I can write it here. So first one is this exactly. Can you do it if you only assume that width at radius 1 is bounded?